Okay. Thank you, Brandy. And thanks everyone for taking time in your evenings to join this talk. It's my pleasure to be with you all. I love it that you have this mineralogy group, this prominent mineralogy group, educating the public and trying to get more people interested in the field of mineralogy, which is, obviously one of my passions in life, which is why I work at the Gemological Institute of America. So today, I'm going to give a little bit of a background on one of the most important gemstones, one of my favorite gemstones, rubies and sapphires, the gem mineral corundum. So I will start off here. Now, this is just a big overview of the different types of colors we can see in corundum. There's a huge variety and diversity of colors in corundum, in sapphires and rubies. For your bit more background, a ruby is the red gem variety of the mineral corundum. And a sapphire is basically everything else. If you only say sapphire, it's meant to understand it's a blue sapphire, but sapphires can be any other color as well. But if it's another color, you qualify the term sapphire with the color. So it's a yellow sapphire or a green sapphire. And this is just a quick overview of the different causes of color in corundum. So ruby, you probably know, ruby is colored red by the presence of chromium. And we're going to go over this all in more detail. We have blue sapphires that are colored by iron and titanium. Yellow sapphires colored by either iron or magnesium, plus a so-called trapped hole, and I'll talk about what that means later. And then we have other colors where we have mixtures of different chromophores. We call these things chromophores. So anything that is present in the gemstone causing color is called a chromophore. So if you mix different chromophores together, you can get a lot of the other colors that we see in gem corundum. So green is a mixture of blue and yellow, of course. So we get green from titanium and iron pairs plus extra iron. Purple or violet is caused by the combination of blue and red, of course. So we get iron, titanium, and chromium causing purple or violet. And we get these weird color change sapphires, which I'll talk a little bit about as well, which might have iron, titanium, vanadium, chromium, a whole bunch of different things going on. Now, you could just stop the talk there, I guess, because that's kind of an overview of the different colors in sapphires, but that's not really a very interesting talk. So I'm going to go into a little bit more depth and of a couple of the more interesting aspects of color in sapphires and rubies. If you're interested, though, in the specific chromophores in rubies and sapphires, there was a really great article published in our quarterly journal, Gems and Gemology, which is available online at no charge at gia.edu. The spring 2020 issue had this great article called A Quantitative Description of the Causes of Color in Corundum, written by some of my colleagues, Emily Dubinsky, Jennifer Stone-Sundberg, and John Emmett, where they go in very fine detail about the different causes of color in gem corundum and what's going on a kind of an atomic level for understanding color in these gemstones. Now, I'm going to start here because this is a really good overview of how we get color in corundum. So this is a colorless sapphire. And so when we look at the crystal structure, you're also seeing the crystal structure of corundum on the right. The blue spheres are aluminum atoms. The red spheres are meant to represent oxygen atoms. So we have these aluminum atoms surrounded by 6 oxygen atoms in an octahedral coordination. And they're all packed together in this structure. Now, the thing is that neither aluminum nor oxygen on their own in this structure will absorb light. So when white light passes through this colorless sapphire, it doesn't really interact that much with those aluminum and oxygen ions in the structure. And so white light is returned right back out of the colorless sapphire. And you see basically just a colorless sapphire because none of these elements will absorb light. Now, just as a quick overview as well, this is the electromagnetic spectrum. So we think about light as being the light that our eyes are sensitive to, but light really means a lot more than that. We have the wavelength range from about 380 to 780 nanometers. That's about the range that our eyes are sensitive to. So those are the colors that we can see in the electromagnetic spectrum. But it extends beyond that, above and below those wavelength ranges. So of course, below, at smaller wavelengths, we have higher intensity light. We have ultraviolet rays, X-rays, gamma rays. At longer wavelengths than red, we have infrared, radar, and so on and so forth. But it's this very specific portion of the electromagnetic radiation spectrum that I'm going to talk about today because this is visible light. So we go from violet to blue in the 400 range of nanometers of light, going into green and then yellow and orange and red at longer wavelengths around 700 nanometers. So we have this device in the laboratory called a visible spectrometer. And so it's basically what it does is you shine light through a stone, and then the light shines into a detector that's capable of detecting how light is absorbed differently at different wavelengths. So when I shine the light through the stone, if I took this colorless sapphire and put it on my spectrometer, I would get an absorption spectrum that looks like this, because none of that visible light is being absorbed by the stone. However, let's say I take a ruby. What's happening with ruby is that I'm taking some of those aluminum atoms in the structure and I'm replacing them with atoms of chromium. Now all of a sudden, I get this deep, rich red color in my gem corundum. So what's going on here? I take the same stone, put it in my visible spectrometer, and I get a spectrum that looks like this. It's obviously way different than we saw with that colorless sapphire. I get these two big bumps at about 410 nanometers and about 550 nanometers, related to the chromium that is now all of a sudden in the structure of my corundum. So these chromium atoms are responsible for this selective absorption of light. The chromium atoms will selectively absorb light at 410 nanometers and 550 nanometers, and this creates what I call a transmission window. So this squiggly line here, you'll see when the values of the squiggly line are high, that means the stone and the chromophores in the stone are absorbing all of those wavelengths of light. When it's low, all of those wavelengths of light get to pass through the stone. And so when we have these very low absorption values, those are the colors that our eyes see, because those are the colors that are allowed to transmit through the stone and come back to our eyes. So this is fundamentally the reason why we have red rubies, because that chromium in the structure of the selectively absorbs blue and green wavelengths of light, allowing all that red light to be passed through the stone. Now I can do the same thing with blue sapphires. So with blue sapphires, I have to have these pairs of iron and titanium on adjacent crystallographic sites in the corundum structure. When this happens, the absorption spectrum looks a lot different than we saw with the rubies. We get this intense absorption band at about 580 nanometers. And this absorption band is kind of broad, and it absorbs a lot of that green, yellow, and orange and red wavelengths of light, and allows all that blue light from between about 380 to 480 nanometers. All that blue light gets passed through the stone, giving us a blue sapphire, of course. So white light comes in, the red light gets absorbed, and blue light comes out. Some of the other chromophores I'll go over kind of a little bit quickly. We have iron 3+ present in the chromium in the corundum structure, causing this nice yellow coloration. And so what we have here is this intense absorption band at about 450 nanometers. It absorbs a lot of the blue wavelengths of light, and the dominant kind of transmission window that we see in this stone is right there in the yellow, causing the nice yellow color in yellow sapphires. Now, green sapphires are a little bit different. Green sapphires have to have two different chromophores to give them that green color. What we have is the iron 3+, which I just mentioned causes yellow color, combined with the iron titanium pairs, which is causing a blue color. And if you mix the blue and the yellow, in this case, you get this nice green color coming out of these sapphires. And again, these two different chromophores create this transmission window right there in the green, perfectly explaining the green color of these stones. Now, there's another chromophore that can behave somewhat like the yellow chromophore from iron. This is called a trapped hole. A trapped hole is a little bit of a difficult concept to explain, but basically what's happening is that aluminum ions in the corundum structure have a charge of 3. But nature is kind of dirty, so we can put other ions on the same crystallographic site as the aluminum. If we take a magnesium ion with a charge of 2 and put it on the site where the aluminum was, this causes a charge imbalance. And this charge imbalance has to be balanced by something else in the corundum structure. And sometimes what happens is that charge of 2 is counterbalanced by a missing electron on a nearby oxygen ion. Now all of a sudden, I mentioned previously, oxygen doesn't absorb light in corundum, but when you take away one of its electrons, it becomes electronically active and it can start to absorb light, and it can absorb light very strongly. So magnesium in a corundum structure can cause these trapped holes, which are basically missing electrons that can absorb light strongly. You may have heard of this concept of beryllium diffuse sapphires. Beryllium diffuse sapphires are the same situation. This is an artificial treatment where you can induce the same trapped hole coloration by diffusing from an external source beryllium into these sapphires. And so again, we have all this light strongly absorbed at around 480 nanometers, absorbing a lot of the blue, violet, and green wavelengths of light, allowing the orange and red wavelengths of light to be passed through the stone. Now, this leads me perfectly into one of the more interesting color phenomena we see in sapphires, which is color instability. And the reason color instability is important is because there's this certain variety of sapphire called the Podporocha sapphire. I'm not going to ask you to spell Podporocha, but it's this very unusual, very rare version of sapphires that have a pinkish orange to orangey pink color, very highly valued because of their nice pastel peachy kind of color. The prices of these stones are very high in the market. And again, what's happening here is that the Podporocha sapphires are a combination of two different chromophores. We have the chromium giving a little bit of a pinkish color to the stone, and we have a trapped hole color giving a little bit of a yellow or orange component to the color of the stone. And so when we combine these in just the right ratios, we get beautiful Podporocha sapphires. Now, the problem with Podporocha sapphires is that this trapped hole coloration can sometimes be unstable. So it's been well known for a long time that we can take some sapphires and artificially irradiate them. So in this case, they used a gamma ray source to irradiate this sapphire. This is actually a very interesting case. We were doing some studies back in the early 2000s when there was this anthrax scare. And then the USPS has started experimenting with using gamma rays to neutralize potential packages of anthrax that were being sent in the mail. And so people also in the gemological community started to wonder if this might affect the color of the stones. And so these were some sapphires that back in the day, they sent these through an experimental USPS artificial irradiation process in order to determine if the color might change, and it did in fact for these sapphires. So some sapphires will have unstable coloration that can be induced by artificial irradiation. You can use X-rays as well, but the big problem is that you can also use simply long-wave ultraviolet light. So with one of these color unstable sapphires, you can shine an ultraviolet light on it, this long-wave UV lamp, and change the color pretty significantly in a short period of time. So like I said, this has been known for a long time. This is a note from 1969 where they were talking about X-ray bombarded sapphires and the instability of this color that can be induced in this artificial irradiation. Now, the nice thing is that in the gemological laboratory, we have a solution for this, and that's to do what we call a stability test. A stability test is simply shining a very intense source of visible light on your color unstable sapphire to remove the unstable component of that coloration. So we use a fiber optic bundle box in the laboratory. It's a 150 watt incandescent light. And the visible light in this fiber optic source can take out that unstable coloration and bring the stone back to its original color. So that's kind of shown just schematically here. We took our artificially irradiated sapphire, we shone a bright light on it, and it came back to its natural color. Now, the thing is, this is not so much of a problem for yellow sapphires. We don't see this very often anymore. However, eventually people came to realize that they could take some pink sapphires, and some pink sapphires also have this unstable coloration to them. So you can shine a long-wave ultraviolet light source on some pink sapphires, induce an unstable artificial orange component to the color, and turn a pink sapphire into a Podporocha-like color. Now, the Podporochas are much more rare and much more valuable than a pink sapphire. So people were realizing that they could do this artificial treatment and kind of artificially enhance the value of their stones. And if you didn't know what you were getting, if you didn't know that that was an unstable coloration, you might be duped into buying one of these sapphires with this unstable coloration. So with pink any possible Podporocha sapphire that comes through the laboratory is going to automatically get this color stability test in order to fade it back to its original color. So this is just shown here. These are some examples of some stones that have come through the laboratory, the color as submitted and the color after the stability test, just showing you the range of colors you can expect to see for these possible Podporocha sapphires. So on the left, the stones came in the range of Podporocha sapphires, and on the right, you can see that after the stability test, they faded completely out of the range of Podporocha sapphires. So these stones had probably been juiced up with a long-wave ultraviolet light before being submitted to the laboratory, and we were able to catch it with the stability test. And now I'm going to kind of take a little bit of a detour here and make this statement that the phenomenon we're seeing here is called tenebrescence. So tenebrescence is something that we know about in the mineralogical community. There are several examples of this in the mineralogical community. The way most people might encounter the phenomenon of tenebrescence, though, is with photochromic glasses. So these are the glasses where if you go outside, they turn into sunglasses, and you go back inside, and the color fades away, and they turn into ordinary colorless glasses. What's happening is that when you walk outside, the ultraviolet light in the sunlight that we're seeing is charging the glasses up, causing an unstable coloration in them. And then as you go inside, that unstable coloration fades away, possibly with the interaction of light from the indoors lights. It's the same phenomenon we're seeing in these color-changing sapphires. I just wanted to show another photo of this. Apparently, they're making these photochromic glasses in different colors now. I like the blue ones. The blue ones are pretty cool. I'm thinking about getting myself a pair of those. But in the mineralogical community, or at least in the gemological community, we know of this phenomenon as well in other stones. The most commonly encountered variety is hackmanite. Hackmanite is a sodalite mineral. It's commonly known to have this phenomenon of tenebrescence, where if you take the stone and expose it to UV light, it will gain this intense purple coloration. So on the left is the uncharged version. On the right is the version of this hackmanite after it's been exposed to an intense ultraviolet light source. Now, exposure to standard white light, same with the sapphires, will cause the color to fade away in a matter of days from these unstable coloration hackmanites. Now, the other interesting thing about tenebrescent stones is that they almost always have this strong fluorescence as well. So when they're exposed to intense long-wave UV light, they almost always have this very intense fluorescence. Is usually orange, yellow, or kind of a red coloration. So this is another hackmanite in its uncharged state, in its charged state, and then again with exposure to long-wave ultraviolet light. I don't know if the sunglasses do this. I should actually check with some of those photochromic sunglasses. It might be interesting to see if they're doing that. But this fluorescence with long-wave ultraviolet exposure seems to be intimately linked to the fact that the long-wave ultraviolet light also changes the color of these tenebrescent stones. So this fluorescence is also seen in tenebrescent sapphires, as shown here. Some colorless sapphires. These are all synthetic sapphires, but some of them would charge up with exposure to long-wave ultraviolet light, and that would be the ones on the right. So those two stones on the right have a strong yellow fluorescence. This is very common for tenebrescent sapphires. Okay, just another example of fluorescence in some tenebrescent stones. These are some more hackmanites. I just want to show another good example of this in the uncharged state. In the charged state, you can see they're getting darker in color, and you can also see that fluorescence. And you also see the intensity of the fluorescence does in some way seem to be related to the intensity of the color change we see in the stones. For instance, that stone, the long oval on the left, has a very strong fluorescence, and it also seems to be one of the stones that is changing color more intensely than the other stones in this case. Some other examples are tenebrescent zircon. So we do see tenebrescence in zircons. A lot of zircons will gain color from UV exposure. And then the interesting thing about the tenebrescent zircons is they also seem to gain color by sitting in the dark. And this is actually kind of the opposite case of what we see with the sapphires, which I'll get to in a little bit. Tenebrescent sapphires will lose that unstable coloration when they're sitting around in the dark. Tuctapite is another example. We don't commonly see it in gem varieties, but we do see a lot of nice mineral specimens. This is a rare mineral from Greenland. It comes from one single source in Greenland. It gains intense red coloration with exposure to UV light, and it can even gain color by exposure to daylight after sitting in the dark. And there's a nice photo of the fluorescence we see in Tuctapite. One kind of other weird example is scaplite. Some scaplite is tenebrescent, and the interesting thing about scaplite is that this tenebrescent color fades within seconds. So if you shine a UV light on one of these rare tenebrescent scaplites, the color will fade away within a few seconds, and you won't be able to see it again. It'll go right back to colorless very quickly. So again, I'm making the case that these unstable coloration sapphires are tenebrescent sapphires, and that's because they gain color when we expose them to UV light, and they lose color with exposure to visible light or when left in the dark. And so this is another example here of one of the stones submitted to the lab in pod paracha color, and then after the stability test, it faded back to pink. Now, one of the interesting parts of this phenomenon, though, is that in some cases we've seen the exact opposite effect. We put these stones in our standard stability test, expecting that either the color would stay the same or we might lose some of this orange color in the sapphires. But in some rare cases, we put these stones in the stability test in our intense incandescent light and notice that they gained a lot of color after the stability test. This is an example here, a sapphire submitted to the lab that was put into the stability test, and it gained a lot of orange coloration afterwards, which was completely unusual. We didn't understand what was going on for the longest time. This is another good example. This was a stone that we were able to purchase for some experiments. We were able to purchase it because it's a beryllium diffuse sapphire, so the price wasn't so high. But it's a sapphire that was submitted to the stability test, and then it gained coloration after it was submitted to the stability test. So we got it in this purplish pink state. We put it into the stability test, and it turned into a pod paracha-like color, a very beautiful color. And so this is showing the full range of colors we can expect to see for some tenebrescent sapphires. When the phenomenon is very intense, we can go all the way from a purplish pink color in the ground state to a pure orange color after it's been charged with intense ultraviolet light. And what I mean by the ground state can be reached either by leaving it in the dark for an extended period of time, or with intense exposure to intense LED light, which doesn't have any UV component to it, or by heating the stone to about 200 degrees Celsius. And so here's what's happening. Again, I mentioned we're going to talk a lot about spectroscopy in this talk. This is a view of the different states, the different charge states of this tenebrescent sapphire. So the ground state is shown in blue, with the lowest absorption. And as we're increasing the amount of this unstable coloration in the stone, we go from the fade tested stone in orange, excuse me, to the color after letting the stone sit in daylight for an hour, to the UV charge state. You can see the absorption is steadily increasing as the orange coloration is going up. Now the spectrum on the bottom is what I call the difference spectrum. So I subtracted two of these spectra to see what chromophore was changing as it was being charged. And this chromophore is actually what I called the trapped hole coloration chromophore. So we're able to induce this artificial, unstable trapped hole coloration in these sapphires with exposure to UV light. So again, we can see the similarity in these two spectra here. We get an intense absorption band at about 480 nanometers, causing this unstable coloration. This is another really cool example. This was a stone I got from the GIA Museum. We have a museum here that has a lot of nice reference materials for us to work with. And I got this sapphire that was labeled from the museum as a pod paracha sapphire. And I looked at it and I said, there's no orange color in this stone. So something weird was going on. I suspected it might have been one of these unstable coloration sapphires that had been sitting in the dark for a long time. So if you took a tenebrescent sapphire and let it sit in the dark for a long time, its color would fade all the way down to pink. So I put this stone in what I call our stability test. I exposed it to that intense incandescent illumination, and it did charge up into a pod paracha-like coloration range. So what was going on was that this sapphire had been sitting in the dark so long it lost all its color, and after being put into the intense incandescent light, it gained its color back. And what was going on is that the incandescent light actually has a small amount of UV light in it. So even though it's mostly visible light, there is a little bit of UV component to that incandescent light that we use for our stability test. And that small amount of UV is able to partially charge this unstable coloration in this sapphire, while at the same time the visible light is partially uncharging that unstable coloration. And due to the different kind of levels of UV and visible light in that light source, we're able to maintain a partially charged state for these sapphires. And the same is true when you expose the stone to ordinary daylight. Another interesting aspect of this story is that this phenomenon has in some way been known by gemstone treaters. So a lot of these sapphires are treated by putting them in a furnace and heating them at very, very high temperatures. This is a heat treatment facility in Sri Lanka where a lot of these sapphires are mined, where they're doing a lot of the treatments on these sapphires. You can see on the right, a crucible of sapphires, yellow sapphires specifically, have been pulled out of the furnace at high temperature. They're still glowing hot orange. And what the burners have learned over the years from trial and error, or who knows how they knew how to do this, but what the burners have learned is that after they take those yellow sapphires out of the furnace, they know that they have to put them in intense sunlight for a few hours, and the intense sunlight can darken the color of these yellow sapphires after heat treatment. So it's a little bit subtle, but I think you can see it here. On the left are the stones that were pulled out of the furnace right after being pulled out of the furnace. On the right are the same sapphires after sitting in the sunlight for a few hours. And so you can see there is a darkening of the color overall in the photo on the right compared to the photo on the left. So here's a schematic diagram I put together of what's going on in these tenebrescent sapphires. We have on the left the fully uncharged state, on the right the fully charged state. We can get to the fully charged state, but with intense exposure to intense ultraviolet radiation, gamma ray radiation, X-ray radiation, and we can partially get to that charged state with exposure to white light that has some UV component in it. Now we can get to the uncharged state by exposure to visible light without a UV component. We can heat the stone up above 200 degrees Celsius, or we can let the stone sit in dark for a couple weeks, and it'll get back to that fully uncharged state. Now this brings us to a challenging question in the gemological laboratory, which is what is the color of the stone? We can go from purplish pink all the way to straight orange, and everything in between. And with different types of illumination conditions, you can have a different stable color in that specific illumination condition. So what's the true color of the stone? In the gemological laboratory, we use daylight essentially as kind of a standard illumination, as the holy grail of illumination. We try to get our standards as close to daylight as possible. So we hypothesized and we posited that the color of the sapphire after exposure to daylight should be essentially the true color of the stone. And we also noticed that the color after exposure to intense incandescent light is very similar to that from what we see with exposure to daylight. So we use the color after the stability test, after that intense exposure to incandescent illumination, as essentially the true color of the stone, because on our reports that we issue for gemstones, we have to issue a color, and so we have to be able to choose what the actual color of the stone is. And so the stability test is our new standard for determining the true color of these tenebrescent sapphires. Oh, so this is I left this slide in twice. All right, another interesting color phenomenon I'm going to go over is back to the blues. So we go back to the blue sapphires, and we again have blue coloration in sapphires coming from these iron titanium pairs on the crystallographic lattice, causing that blue transmission window by strong absorption of light in the yellow, orange, and red region of the spectrum from this iron titanium intervalence charge transfer band. Now, some sapphires can also be treated to enhance this blue coloration. So we saw with the trapped hole color, the unstable trapped hole color, in many sapphires you can induce that unstable trapped hole color through artificial treatment. And the same is true for a lot of sapphires. So this is an example of a sapphire from Montana. This is a Rock Creek sapphire. This is a stone we heated in our laboratory. On the left, the original stone unheated with a very kind of pale color, a little bit of a yellow coloration, and on the right is the dramatic change in the color we see on the same stone after treating the stone at heating it up to very high temperatures. This is shown spectrographically here. The blue color line is the color of the spectrum of the stone before heating. The orange line is the color of the stone after heating. So you can see this dramatic change in the spectrum as well. And again, we have the growth of this absorption band at 580 nanometers after treatment of the stone. So we know that we're inducing these iron titanium pairs by heating the stone. Now here's a view of the same stone through the microscope. So on the left, what you're seeing is this cloud of what we call silk. Silk is a gemological term we use for very small microparticles of inclusions within these sapphires that oftentimes take on a needle-like or a kind of a slender needle-like appearance to them. And you can see that on the left. These micro-inclusions, this silk, is the mineral rutile. So rutile is the mineral composed of titanium and oxygen. It's a titanium oxide, and it's very ubiquitous in a lot of sapphires. Almost all sapphires from around the world will have some kind of silk. One of the few exceptions is the Yogo sapphires. Don can tell you a little bit more about that later if he's on the call still. Yogo sapphires don't really have much silk, but most of the other sapphires in the world do, which means that the silk is part of the heat treatment process. So when we're heating the stones, we're trying to take the titanium from those rutile microparticles and put it into the corundum lattice. So by heating up these sapphires, we can dissolve that rutile silk, put it into the corundum lattice, And by introducing titanium into the corundum lattice, we can also create these iron-titanium pairs, which is causing the blue coloration in these sapphires. Here's a little bit of a view of what's going on. So this is a more typical furnace you would see for heat treatment of like the Montana sapphires, for instance. This is a modern resistance furnace, electrical resistance furnace. So we have this guy. This is a miner of sapphires up in Montana, but he also runs a heat treatment facility for the Montana sapphires. If you ever go to Gem Mountain, you might meet this guy. He runs the Gem Mountain tourist feed digging operation up there, and he'll heat your sapphires for you if you find some nice sapphires up there as well. This would be the furnace he would be using for that. So he's loading up his sapphires into the hot zone of that furnace. You typically, for these blues, you need to heat the stones up to about 1500 degrees Celsius in order to get the stone hot enough to dissolve the titanium, to make the titanium move throughout the corundum lattice, creating that blue coloration. And here's a view of what you would see before and after. So this is the same parcel of sapphires in the crucible. Then as he's pouring them out, you can see the dramatic change in color. The stones have gained a lot of blue coloration through this heat treatment process. I'll run through just a couple more examples. This is one that was another Montana sapphire from Rock Creek with these dense patches of blue, dense patches of brown coloration after heat treatment. Those rutile patches dissolved in the corundum lattice, creating the deep blue color. And a photomicrograph showing the effect of what's going on. So we see these nice patches of silk. It's so dense, and the particles are large enough that we have this nice brown coloration coming off of these. As they dissolve into the lattice again, we get this nice blue coloration coming out. One more example, just because I really love this stone. This is a really cool stone. This was actually from the Dry Cottonwood Creek deposit, which is also in Montana, but it's not currently being mined so much these days. A lot of the Dry Cottonwood Creeks and a lot of the sapphires from the other deposits will, in Montana, will develop these nice yellow cores after the heat treatment process. In this case, we developed a nice yellow core and also has silk in the rim of the sapphire, giving this nice kind of party-colored sapphire. All right, one final phenomenon that I'm going to go over before wrapping it up and taking some time for questions is color change. So there are some sapphires that have this other type of color change, which is not really related to the tenebrescence mentioned earlier, but a color change when you can see colors in different types of illuminants. So we can think of like warm and cold colors, right? So we think of warm incandescent lights, the kind of lights you want to have in your house to create a nice warm lighting environment. The fact that they're warm means that the color is more heavily tilted toward the yellow and red wavelengths of light, compared to what we like daylight, for instance, is more of a cool color, which means it has a higher intensity of blue and violet wavelengths of light in the stone. And so with color change stones is that we have two transmission windows, one in the red and one in the blue. In this case, the visible absorption spectrum shown here is a product of the combination of chromium and iron titanium pairs. So we have the chromium bumps at 410 and then 580 nanometers. 410 nanometers combined with
indoor. Is that?
Sorry. So we have the chromium and iron titanium pairs. The iron titanium is absorbing light strongly at 580 nanometers, causing the blue color. And the chromium ions are absorbing the rest of the light, giving us the red transmission window. So the fact that we have these two transmission windows through the sapphire, one in the blue and one in the red, is what's causing this color change between these two different illuminants. So a cooler light source like daylight is going to heavily favor that blue transmission window, whereas a warm light source like incandescent light will more heavily favor that red transmission window, causing these two colors in the sapphire between these two illuminants. And that's kind of shown here, again, another good example of this. This stone that goes from kind of a violet blue in daylight to more of a violet purple color in incandescent light. So we have the combination of chromium and iron titanium pairs causing these two colors in these sapphires. So again, we have the two transmission windows giving us these two different colors. Now I can take the same sapphire, the same spectrum, and I can do a chemical analysis on it, just to kind of break this down. And I know how much chromium it takes to give you a certain amount of a contribution to the spectrum, and I know how much iron titanium pairs it takes to give us a certain contribution to the spectrum. So I can mathematically try to recreate the absorption spectrum in this case, using the chemistry that I measured on this sapphire, to get an idea of how much chromium and how much iron titanium pairs do we need to give us a color change like this. So this sapphire had basically 4 parts per million iron titanium pairs and 40 parts per million chromium pairs. And I can see the green spectrum here is the mathematical summation of those 2 chromophores based on the chemistry. We can see we can get a pretty good fit to the absorption spectrum of this sapphire. So meaning that this color change we're seeing is very well explained by the presence of these 2 chromophores. Now, we actually see some other unusual types of color change in some other sapphires. I love Montana sapphires, so I'm going to focus a little bit more on some other Montana sapphires as well. These are some really cool Montana sapphires with an unusual color change. So a lot of the color change in sapphires we see is from kind of blue to purple or blue to violet. These ones went from pink to green or pink to kind of a violet color or pink to a orangey brown color. And so something else was going on in these sapphires. And again, I took a chemical analysis. You see the chemical analysis up here in the corner. These sapphires can't be explained simply by the presence of chromium and iron. Sorry, the presence of chromium and iron titanium pairs. We need something else to explain this as well. So what I was able to do, this table shows you a calculation I made. So we can also, if we know the chemistry of a sapphire, we can mathematically create the spectrum of that sapphire. And then I can also mathematically predict the color that might be produced by that color, by that spectrum. And I can do it also individually for each of the chromophores, and I can add the different chromophores together to see what the color change is being caused by. So the total color is shown here between daylight and incandescent light for this color change sapphire. These boxes in the top, the first row, are the modeled colors for the spectrum that I measured and the chemistry that I measured. And then I have all the other chromophores here. So chromium is giving a pink color, but again, not much of a color change on its own. There's not much iron titanium pairs in this sapphire. And then the iron 3+ atoms on its own is also shown here. But none of these individual chromophores on their own is producing much of a color change. What I'm showing on the last one, the bottom, is when I combine chromium and iron in this sapphire. When I do that, then the combination of these 2 chromophores does give us this nice color change, which we can see by the modeled color based on these 2 chromophores, which is pretty well matching the color of the stones. One more example of this, another one of these color change Montana sapphires going from green to a brownish pink color. And again, I can model pretty accurately with the total chemistry of the sapphire, and then I can look at the individual chromophores in the sapphire as well. What I notice is that in this case, again, it's probably the combination of chromium and iron ions that is causing the change in color between these two illuminants, the daylight and the incandescent light. So that's kind of what I had to go over with color phenomena in corundum and rubies and sapphires. I have some time available left if anybody has any questions or wants to chat about anything. So thanks again for tuning in.